Okay, so this will be the next lecture video on combinatorial methods in constructing covering arrays. So this should be a rather short video. I don't want to get too deep into the math here, but uh, there's a lot of literature that you can go down into here. I'm just going to give a very brief overview of some techniques that are used in the construction of covering arrays. So the basic idea behind these is that you can think of these as just a way of plugging a formula or some expression and just out pops the array. So you don't have to do any real computation here. All that you need is just to plug in various values, and if some of the parameters for covering arrays are at least a certain number, or at most a certain number or something, then we can guarantee a covering array exists and is very often good. So let me turn off that. Okay, so let's get into this. So one technique is to use something called a transitive group, or apply the action of a group. So a group, a group is a set of elements. Let's just call them V. So I'm just going to give the general definition of a group. So there is, and it has certain properties. So there's an identity, and I'm going to call it E, which is an element of the group. It has inverses. So for every A in V, there is an element B such that A times B is equal to the identity. And there's an operation I'm going to call a circle with a dot in it. So it could be our usual definition of plus or times, but it's just a way of taking two elements and out popping another element. So you take two elements, you apply whatever the operation is, and then you get a third element. So what I'm saying here is that for any element in the group that you want, there is another element, maybe the same one, such that if you apply the operation in that order, A dot B, then out pops the identity. There exists some element. There's an inverse for it. The group is associative. So associative. So what does that mean? That says that if I do A with some operation applied to the result of some element B applying the operation with C, then basically what this says is I can move the parentheses around. So I can do A dot B first and then dot C afterward. And it's closed, which means that if I apply A dot B, it's always within the group. So if I apply the operation to any two elements, you always will get some element of the group. You never leave the group. So for example, an example of a group is the integers. So the integers are a group under plus and minus, and that's it. So why is that true? Well, is there an identity? So the identity, then can't spell identity. Identity E is 0, because if I add 0 or subtract 0 from anything, it doesn't change anything. Oh, that's one thing I should have said. So what does identity mean? Identity means that if I apply the operation to any element, then it's the same thing as applying it in the reverse order, which will be the original element. So if I apply the operation to the original element with the identity, nothing changes. So in the group of integers under addition or subtraction, the identity is 0, the inverse of A is minus A, because if I, so that's for plus. So what would the one for subtraction be? Well, how do I get the identity from any element? I just subtract the original one. So the inverse of A is just A for the subtraction operation. And is it associative? Well, let's see. So it is associative for plus because A plus B plus C under integers is the same thing as A plus B plus C. But let's check if it's associative for minus. Well, A minus B minus C, well, is that the same thing as A minus B first minus C? Well, let's see. Well, the left-hand side is A minus B minus C, plus C, sorry. And check that if that is equal to A minus B minus C. And we see, well, no, they're not the same because we have a plus C on one side and a minus C on the other side. So in fact, it is not a group under subtraction. So it's only a group under addition. It's not a group under multiplication because there is no inverse for 2 under multiplication. And what would the identity for multiplication be? It would be 1 because, well, that's what I would want it to be. So that because if I multiply by 1 by anything, I still get the anything back. So because there's no inverse for 2 under the multiplication operation, the integers are not a group under multiplication. Another example would be the rational numbers but take away 0 under multiplication. That would be a group because the inverse of an element in the rationals would be just the reciprocal of the number. And it's associative because we can multiply things in any order. So there are some groups, things that are not groups, and some additional properties that you can get. So what are we talking about here? So a one factor for a graph with 2 n vertices is n disjoint edges. So what that means is that we're going to pick n edges and involve every vertex of the graph because they're disjoint edges. Oops. Yeah, they're disjoint edges. So what we're going to use here is something called a one factorization of a graph, and it has to be not necessarily R regular, but it has to have at least the minimum degree has to be at least a certain number. So you just partition the graph into one factors. So the idea there is you find a factor, a one factor, you take it away from the graph, you find another one factor, you take it from the graph, etc., until you have removed every single edge. So so basically you just have a bunch of one factors that together make the original graph. So why is this useful? So let's talk about this graph right here, which is the complete graph. So this is the complete graph on 2n vertices. So that means that we have a bunch of vertices, and every possible edge is there, every single one. That might not look pretty, but every single edge is there. And it has a one factorization, and here's a simple way to actually do it. So I won't go through the details of what that is, but I invite you to actually check for yourself that that really is a one factorization, because each of these right here is a one factor because we involve every single vertex and we don't have edges that that intersect each other, because the first one involves infinity, and adding two finite numbers never gives infinity, and the ones in the second part are disjoint purely because of the arithmetic modulo 2n minus 1. So you're performing arithmetic here, and you're guaranteeing that they will that two edges will never involve the same vertex. So it is a one factor, and because every single vertex is in there, and just apply this over and over and over for every single other vertex and starting vertex I, and you will get a one factor for all the way around, which will give you a one factorization. So why is one factorizations useful? So the basic idea is that they allow us to make covering arrays. So the first part of this is to form an array. So this is not a covering array. So this is not a covering array, but it will help us get one later. So here's the array is almost a square array. Well, here what we have are the vertices as denoted by the columns, and the one factors are going to be the rows of this array. Okay, so what we're going to do here is, let's just say that we have picked vertex I and one factor j. So this is, so right here is vertex I and factor j, ordered however we want it. As long as we have a fixed order, then that's fine. So what we're going to do is we're going to, so what we're going to do is, for the factor j, we're going to order the vertices as vj1, vj2, etc. up to vj, let's see, 2n, because every vertex appears in every one factor by the definition of one factor. So let's just say that vertex I is right here in this list. We can order this list however we want as long as we keep it fixed. Then what we do is, in this position right here, we're going to put the index on factor j's list. So wherever vertex I appears on this list, I'm going to put that number in there. So this array has some nice properties that we will exploit when we make a covering array. So it is possible to prove that there is a row that has all different symbols. It doesn't say what those symbols are or if it has every possible ordering, but we're going to consider that. And in the first three columns, they're based on the construction that we did before. There's a row where the first two columns have the same symbol, but the third one is different. So, and what do I mean by this notation? This means that no matter if I, j, and k, no matter what values they are, as long as the set is 1, 2, 3, which means that I could be 3, j could be 1, k could be 2, as long as all three of them together make the set 1, 2, 3, then that's fine. So that means that in the first three columns, we guarantee that we have this property that let's just draw it out. So we have an array right here that we just made, and let's look at the first three columns. Let's just say these three. And then what we guarantee is that let's just look at the case when I is 1, j is 2, k is 3, which means that in the first two columns, we're going to get a value that's the same. So like say 0, for example. And then in the third one, we will have a different value there. Let's just say 2. And then In the second scenario, maybe we have I equal 2, j equal 1, k equal to 3. Then what this says is that, again, I and j have the same value and k has a different value. So maybe let's instead look at a different example where let's just say I is 3, j is 2, k is 1. So this says that in columns 3 and 2, they have the same value, maybe in a different row. Actually, it has to be a different row. And K, which is the first column here, has a different value, let's just say 3. Then, so that's what we can guarantee about this array. We can't guarantee necessarily any more out of this. Okay, so what are we going to use here? What can we actually use out of this? So, so I'm not going to go all into the details here, but the fact that if n here, which was the number that was used in making the graph, so remember we had the graph k2n, so if n minus 1 happens to be a prime power, then there's a certain type of group with a really nice property. So I'm not going to really talk about what this actually is, but it has a really nice property, which means that based on certain multiplication rules, we can guarantee certain properties about the group itself. So this is something called the projective general linear group. And so it looks like PGL2 of n minus 1. That's what you will see. And so why is prime power important? So this is based on, so it's not actually, but it's based on, yeah, so it's not actually a finite field, but it's based on a finite field. So this is based on something called a finite field, which only, so the finite field only exists for prime n or a power of a prime. So if the order of the group, which means the number of elements in the group, so if the number of elements of the group is a prime number or a power of a prime, then the finite field exists, which means that the projective general linear group exists because it's based off of the finite field. So if it's n minus 1, that's a prime power. If n minus 1 is a prime power, we add an additional element which happens to be infinity. So there's a fixed element at infinity, which is where this word projective comes into play. So projective just means that there's some element at infinity. Okay, and if you look up what this group actually has, it has a bunch of elements in it. So if you provide the number n, you have roughly n cubed elements in there, a little bit less. So what do we do with these? So let's just say that the elements are, let's just say v0, v1 up to vm, where m is that giant number n times n minus 1 times n minus 2. Then what we do is we take that array that we had before and we apply v0 to that, basically every element of that array that we constructed before by the action of the group. So remember that the group will always tell you take two elements and out pops another element of the group. So what you do is you just apply v0 to every single element of this array, and then you get that array. You get an array back with different elements, obviously. Then what we do after that is we do the same thing, but now with v1, with the same element, with the same original array here. And then we do this same idea with v2, and then etc. up to vm for all of the elements in the projective general linear group. So each of these initial, these arrays right here, before that we apply the element of the group, these are all originally the array constructed before. So we take the array that we constructed before, apply, make a bunch of copies of them, apply each of the elements of this giant group here to each of the copies, put them all vertically on top of each other, and what we can guarantee based on the structure of the group and the fact that it has this special property called the three transitive action, actually sharply three transitive, we can guarantee that every single three-way interaction appears except when all the ones of the form like 0, 0, 0, 1, 1, 1, 2, 2, 2, up to n minus 1, n minus 1, n minus 1. So all of the interactions that have the exact same value in each place, those don't appear. So what we do at the bottom down here, or I guess anywhere, is we put in a row of all zeros, a row of all ones, and then a row of all twos, etc. for all of the elements in the from 0 to n minus 1. So what we get then is the number of rows that we constructed. Well, we had 2n minus 1 originally for each of the original arrays, and for each of them we applied them to each of the elements of this giant group. We added n rows on to get the final, so these are the final n rows. Because we didn't cover those interactions, we have 2n columns because that's the number of columns originally and we didn't add any, and the number of values is n because that's what we started with anyway. Okay, so that's basically a way to get a covering array of strength 3 for any prime power. But one of the main problems with this, it does work, but the problem with it is that the prime powers are quite sparse. So if you go to very, very large values of n, you're not going to find many prime powers, so this method doesn't guarantee to work. And these types of groups or fields don't necessarily exist for values that are not a power of a prime. So I invite you to do this example, so I'm not going to go through it, but you can actually just go through this example. So n is 3, so n minus 1 is 2, which is a prime, which is good. So therefore we can apply this method. So then you work with k2n, remember, which is k6, which means that we have 6 vertices right here, and each of the possible edges is present. I don't think I'm going to be able to draw them all, but I think that's all of them. I don't see any others. So what you do is you apply the method, then you get factor 1, 1 factor 1, factor 2, factor 3, factor 4, factor 5. So you're going to get 5 factors out of this thing. And then, as a result of that, remember that we have 2n minus 1 rows in the original array and 6 columns. So 5 rows and 6 columns. So the projective general linear group with parameters 2 and 2, the 2 comes from the fact that it's n minus 1. This 2 right here is something different based off the group. It's purely based on how we actually construct it, so don't worry about that too. The second 2 is based on the order of the n that we have here. So it's isomorphic to the symmetric group on 3 values. Again, I'm not going to go through this, but basically this group has 6 elements in it. So that means that if let's just call them v0 through v5, then what we'll do is we'll apply v0 to a copy, v1 to a copy, etc. up to v5. and then adding the row of all zeros, row of all ones, row of all twos, because there are only 3 values in this array, will give us 33 rows, because 5 rows for 6 copies each gives us 30, 3 more gives us 33. And for unrelated reasons, this is optimal. For other parameters, it's not necessarily optimal, and in fact, in some other cases, it isn't. But in this case, it just happens to be. Okay, so that is transitive groups. Now let's get on to something called combinatorial design theory. So what is this? So combinatorial is just counting things. Design, what it is basically just a bunch of subsets of a set with certain properties. So the one that we're looking at here is something called a Steiner system. And what we have here is we have a bunch of elements, just like a group, no difference there. But now we're going to pick a bunch of elements of the same size of the ground set V. So let's just say V is 0, 1, 2, 3, 4, and let's say K is 2, then B, which is the set of blocks, will be 2 element subsets of V. So maybe we have 1, 2, and 2, 4, and 0, 3, etc. And we don't necessarily have to pick every 2 element subset. But what we guarantee is that for every T element subset of V, we will appear only in exactly one block. So if I pick, for example, T to be 1, then these blocks are not a Steiner system. Why is that? Because if I pick the 1 element subset 2, well, that appears in 2 blocks, and we require it to appear in exactly 1 block. And, well, every other element appears at least once, so that's good, but 2 appears twice, so that's not possible. So it's not a Steiner system here. There happens to not be a Steiner system that's known for very large T here, so if you happen to find one, please let people know. But we'll give an example right here of how you can use a Steiner system to construct a covering array. So how do you use it? What you do here is, the example we're looking at is, so the first parameter is T, which is 5. So remember, that's 5 element. We want every 5 element subset to appear in exactly 1 block. We're going to have K to be 6. So the blocks are going to be 6 element subsets of V, where V, we can say without loss of generality, is 0, 1, 2, up to 11, because we have the 12 here. So V has 12 elements. Let's just say, for example, there's 0 through 11. So an example of an element that B could have would be something like 3, 6, 7, 8, 9, 10, for example. And we want every 5 element subset to appear in exactly 1 block. And what we can do here is to take every 6 element subset. And actually, I'm not sure about that. I'll have to look at that. But yeah, so here you can actually calculate the explicit number of blocks that the Steiner system can have. So it has 132 blocks in here. Actually, I'll just quickly check that. Yeah, so it's not every 6 element subset. Actually, that wouldn't work, but yeah. So you're picking 132 blocks. This is actually the exact number of blocks that have to exist in order for a Steiner system of these parameters to even exist in the first place. So in order for a Steiner system to exist, what you need is that V choose T divided by K choose T has to be an integer in order for this to even work. So, and in this case, it happens to be 132. So what are we going to do here? So what we're going to do is to construct the characteristic vectors of the blocks. So for example, so let's look at that subset 3, oh, what did I pick before? 3, 6, 7, 8, 9, 10. Then in here, we're going to have a giant array that has 12 columns and 132 rows. And for this one, we'll look at the row, and what it has to be is this. So we're going to have a 12 element row, so 12 elements, and we're going to put 0 or 1 in each position. So we're going to put a 0 if that column is in the block and 1 otherwise. So 0 is not in the block, so we put a 0. 1 is not in the block, so again we put a 0. 2 is not in the block. 3 is in the block. 4 is not in the block. 5 is not in the block. 6, 7, 8, 9, 10, and then 11 is not in the block. So we'll have that row in the cover in this array that we're making. So it's not a covering array yet. Then what we're going to do after that is we're going to form a slightly smaller array, which is all the characteristic vectors of sets of size 2. So this is, so let me just check one thing just to be sure. Yeah, so this is going to be looking at every 2 subset of the 12 elements. So for this one, we're going to have B for A2. So the blocks for A2, so to speak, are going to be 0, 1, 0, 2, 0, 3, etc. up to 10, 11. So every 2 element subset. So every 2 subset of the elements that we have, and we'll do exactly the same thing as what we did before, but now there are only 66 elements because 12 choose 2 is 66. So that was what I was checking. And A3 is going to be the same thing as A2, but what we're going to do is we're going to complement each row. And what do I mean by that? I mean that if you had a 0 in the A2 array, the A3 array is going to have a 1 in that same position. And if A2 had a 1, A3 will have a 0 in that position. And if you put A1, A2, A3 on top of each other, then what we claim is that we will get a covering array out of this. You can calculate that 264 is the number of rows that you get. It has 12 columns and 2 values because we're always doing characteristic vectors, which means that it only has 0s and 1s. But we claim that it has strength 7 out of here. And it's a lengthy verification, but it is possible to do. The idea is that if you have a few number of 0s or 1s, then the A2 or A3 array is going to cover you. But if you have one of the 2 middle values, then what will happen is that you will find a block for which you are a subset of that block, which means that you will be able to be covered in some row. So Steiner systems haven't really been used very recently, purely because you can't just apply the Steiner system and get the array out of it like the transitive group operation we were talking about earlier. But it turns out that they can be used like in this case. Yeah, so if you're interested in that, I would highly recommend looking up Steiner systems. And finally, we'll talk about Hadamard matrices. So a Hadamard matrix is a very peculiar object in computer science and math. And what it is a square matrix, so it's always a square matrix, and each entry in it is either a +1 or a -1. Every position in the entire array is a +1 or a -1. But the property is that if you take two rows or columns because we can transpose the array and get the same property. So what if I just take, say, this row and this one? Then what I do is, let's find the inner product of these rows. So that means that if this is row I, I'll call it Ri, Rj, then what we say is that the inner product is equal to the sum from, let's just say that there are n columns or rows because it's square. So let's go from k is equal to 0 to n minus 1. Let's just say we index the columns from 0 to n minus 1 or something. Then what we're going to do is we're going to take the kth value of the ith row and multiply it by the same thing from the jth row. And we add them all up. So we multiply the same position of the two rows and add up all the results. So let's just say we had minus 1. So here's an example. So minus 1 plus 1 plus 1 plus 1, and 1 minus 1, yeah, let's just say plus 1 plus 1 plus 1. Okay, so let's see. Yeah, so then let's say we have these two rows. Then what we have here is we have, is that right? Yeah, that's right. I confused myself. So let's do the product top to bottom. So -1 times +1 is -1, +1 times -1 is -1, +1 times itself is 1, +1 times itself is 1. And if you add all of these up, we get 0. So a Hadamard matrix is a square matrix where the inner product of any two rows or columns, I guess, will always have inner product 0. And it has been proven that they only exist for either 1, 2, or a multiple of 4. And a giant conjecture called the Hadamard conjecture says that they exist for every order that is a multiple of 4, but that hasn't been proven. So we're going to call a Hadamard matrix T strong in connection with covering arrays if we take the Hadamard matrix H and put at the bottom below it, or I guess above it, minus H. So the array that we're making here is not square because each of the Hadamard matrices is square. But how we're going to use this is we're going to say that this is T strong if we will always yield a covering array out of this. So the number of columns is always n because we're just juxtaposing it vertically, and we had n columns before. We have two values because we have +1 and -1. We have 2n rows because we had n rows to start with, but now we have 2 of them, so it's 2 times that. And I should say -h is we're going to take +1 and replace it with -1 from the original array. And if we had -1 before, we're going to replace it with +1. So you can actually prove that every Hadamard matrix is 3 strong. So I invite you to actually prove this. So so the way to do this is to use the fact that the inner product is always 0. And the fact that you can only get half of the interactions from that fact for one of the arrays, but you get exactly the right half because when you do the complement for -h, you will get exactly the other set of interactions. So that will tell us that every Hadamard matrix is 3 strong. But if you have a suitably large Hadamard matrix, where n is at least 12 and a multiple of 4, because remember again, Hadamard matrices only exist for multiples of 4 when n is at least 4. So if n is at least 12, then you can actually show that such a matrix is always 4 strong. So that's a little bit harder to do. Okay. And finally, there's a very long construction. I'm not going to really go through it, but again, if the number that you're dealing with is a prime power, and in this case it has to be odd, so it can't be 2, then what you do is you form something called the adjacency matrix of what is called a Paley graph, and when with certain properties of Q. And what you do is you turn that back into a Hadamard matrix, and what you can show is that it is T strong for T suitably small. So if T is sufficiently small such that this quantity is less than Q, and the property of Q is still holding, then if you just do this simple operation working with the finite field, I should say this is the finite field, a field on Q elements. And you can actually show that this Hadamard matrix can be any strength strong. So before, we showed that every Hadamard matrix, if it's big enough, will be 4 strong. But here you can get any strength you want. So, and this has actually been improved significantly in different ways, using something called a character argument, which is something that's used in combinatorial design theory. I'm not going to go into that because it's going down too much into the weeds of this, but the fact that you can use a rather simple object called a Hadamard matrix to actually make a covering array shows that it is really important when the number of values is a prime power. You can actually have quite a bit of you can show quite a bit here. When it's a prime power, you have all of these really nice properties, such as a finite field existing, which guarantees inverses, which means that you can actually show that certain interactions must appear. But if you don't have a prime power, then you can't guarantee that those properties exist anymore, which is why one of the projects that I've asked you to do is to find or show doesn't exist a covering array with 100 rows, strength 2, 5 columns, and 10 symbols. And why is this such a problem? Is because 10 is not a prime power. So that's one of the reasons why it's so hard to find a covering array for these parameters. Okay, so that's all I'm going to say on combinatorial techniques. Next on Wednesday, we're going to be talking about cut and paste techniques. So I'll see you then.